In the previous section, we saw that Stokes' theorem was the three-dimensional analog of the circulation form for Green's theorem. Now we need a three-dimensional version for the flux form of Green's theorem. Now Green's theorem is two-dimensional. So you have some enclosed circuit, some closed curve, and you want to find the flux. You want to find how much the vector field is pushing outward across that curve. Then Green's theorem will find that for you. The flux is equal to the line integral of the vector field times the normal curve, or I mean the normal vector. In other words, it's the double integral over the region. The region's the internal portion of the two-dimensional divergence. So this is divergence in 2 dimensions, right? The divergence of the vector field. So now we want to extend that to 3 dimensions. That's the divergence theorem. So it basically takes the same concept. So we have a 3-dimensional object, a 3-dimensional surface, and we want to know how much the vector field is pushing out across that surface, or pushing out from the inner portion of that surface to the outer portion of that surface. All right, so then the flux will be equal to the surface integral now, right, as opposed to the line integral, right? It was a line integral for 2 dimensions, but for 3 dimensions, it'll be a surface integral. In other words, it's the triple integral over the solid of the divergence of the vector field F. Oop, that should have a little F on top of it. And that would be the triple integral of the del operator dot product with the vector field dv. Now, let's just remind ourselves real quick. So recall that the del operator is the partial with respect to x, the partial with respect to y, and the partial with respect to z. So when we want this triple integral for the divergence theorem, that would be take the dot product of the del operator with your vector field. Well, your vector field is FGH. So the partial with respect to x of f. So to be partial f with respect to x plus partial g with respect to y plus partial h with respect to z dv. This is the divergence of f. All right, now let's look at an example. And we're going to do this example, the same example, twice. We're going to do it with the old method that we learned and the new method, the new divergence theorem. So let's begin with the old method. Now, reminder of the old method that we learned when we learned the surface integrals. We learned that there is a surface integral of a vector field. There's a flux integral for surface integrals. And we're going to use that fact. All right, now we have a hemispherical solid bounded above, right, by x squared plus y squared plus z squared equals 25, and below by the xy plane. So when you think about a surface integral, there's actually 2 surfaces. There's the surface 1 that's at the bottom, right? The disk that's in the xy plane. And then we have another surface at the top, which is the hemisphere, right? The half sphere. Okay, so we are going to have to find the flux for both surfaces. So flux, let's actually start. So flux for S1, right? So let's do that. Now, surface 1. Surface 1 is on this plane. Oh, and let's remind ourselves real quick. Flux, when we're doing the surface integral directly, is the double integral with respect to r of f dot n dA. Okay, so let's just leave that right there. All right, so we need to find this surface. So z is equal to 0 is the surface. So let's just say S1, surface 1. Let me do S1. So for S1, z is equal to 0 because we're on the xy plane. All right, so the normal vector is equal to the gradient of W. Now, we're trying to go downward. So we think about this, when we look at this surface, the upper part will actually still be inside the surface. So we need the downward vector, the downward normal. So we're going to let it be 0, 0, -1. And we're doing this because we're going to use downward for normal, right? We're trying to see what's poking out down below this, because poking up above wouldn't do us any good because that's going into the surface. So we're going to pick downward. So we're going to use 0, 0, -1. In other words, we're letting W be 0, take away Z. 0 because we don't have a Z of XY on its own. So if you remember what W is, right, that's how it works. It's Z of XY, which we don't have that surface because it's just a flat plane. Take away Z. So we're going to let it be 0, take away Z. So it's -1. All right, so then our vector field, which is x squared, y squared, z squared, would be x squared, y squared, but instead of z squared, z is 0 on this plane, right, on this surface. So it's 0 squared, right, because z equals 0. And therefore it's x squared, y squared, 0. All right, so now when we want the flux, we want, actually, let me put it right over here. The flux for surface 1 is equal to the double integral of f, which is x squared, y squared, 0, dot product with 0, 0, -1, dA. And we don't even have to find the limits of integration because that's 0, which is 0. So surface 1 has no downward flux, right? It has no outward flux. Done with that piece. All right, so now what about surface 2, the hemisphere, right? So surface 1 was the plane. Surface 2 is the hemisphere. So let me draw a line on my paper. All right, so surface 2, we're going to find the flux. So that would be the hemisphere. Oh, let me write this differently. There, I had to move it because the hole was in my way. All right, so we have our hemisphere. That's our surface 2. All right, now what is the hemisphere? Well, remember, because we're doing this way, we're going to need to find W. W is z of xy minus z. So we're going to need to find our function. So we're going to have to take the hemisphere and we're going to have to modify it. So the hemisphere originally is written as x squared plus y squared plus z squared equals 25. So we're going to solve that for z. So z squared equals 25 minus x squared minus y squared. And because we're looking at the top half, right, z is plus or minus the square root, but we're only going to use the positive one because we're looking above the x-axis. Or above the xy plane, sorry. Above the xy plane. Okay, so there's our hemisphere. So there's z. So now what's W? Well, if we look at the top half of this, we're trying to find upward, right? We're trying to figure out what part of it is poking out, right? Poking out of this hemisphere. So we need upward. So that means we need upward normal. And because of that, we're going to need W to be equal to z minus z of xy. And we're going to have to set it equal to 0. All right, so that means that we're going to take z. W is now z minus this function, the square root of 25 minus x squared minus y squared. Or in other words, it's z minus 25 minus x squared minus y squared to the 1/2 power. Why do I find that? right? Why do I care? Well, because I need my normal vector. The normal vector is the gradient of w, right? Which is wx comma wy comma wz. Now, wx, you'd bring the half down, so it'd be negative a half times 25 minus x squared minus y squared to the negative a half times the derivative of the interior with respect to x, which is negative 2x. You do the same thing for y, negative 1 half 25 minus x squared minus y squared to the negative 1 half times negative 2y. And luckily for us, the derivative with respect to z is really easy. It's 1 because we're going upward. There's your normal vector. Okay, so now we have to put it all together. So we have to take the double integral, right, to find the flux. So S2 flux is equal to the double integral over the region of f, which is x squared, y squared. Now I can't use z squared, right? I have to have only two variables because it's only a double integral. So instead of z squared, I'm going to use the fact that z squared is 25 minus x squared minus y squared. So we're going to use in our vector field right here. Use that fact. So it's going to be 25 minus x squared minus y squared for the last component. And we're going to dot product that with our normal vector, which I'm actually going to simplify this a little bit. The negative 2 and the negative a half cancel, and you're left with x over the square root of this. So that's x over the square root of 25 minus x squared minus y squared. Then y over the square root of 25 minus x squared minus y squared, and then 1. And then I'm going to take that over my region. All right, well, we can put this together and simplify it a little bit. This is going to be x cubed over this. This is going to be y cubed over this, and we're going to add them together because they have the same denominator. So this is the double integral of x cubed plus y cubed over the square root of 25 minus x squared minus y squared. Plus, right? I was about to say times, but it's plus, right? So I did a little bit of double working there. It's x squared times x over that plus y squared times y over that. So they have the same denominator, so they can just get pushed together. And then this is 25 minus x squared minus y squared. Now let's think about this for just a second. What's the region that we're integrating over? Well, what's the shadow that this hemisphere casts onto the xy plane? It's a circle, right? So if we think about that region, R, right? So this is the surface. Actually, it's two surfaces, right? So the surfaces, and then here's the region of integration down here. So that region of integration is a circle of radius 5, right? Because x squared plus y squared plus z squared was equal to 25. And we all know that when you're graphing over a region, a circular region, we should switch this to polar coordinates, which is exactly what we're going to do. So r goes from 0 to 5, theta goes from 0 to 2 pi, and then we're just going to have to substitute in what these are. So this is r cubed cosine cubed theta plus r cubed sine cubed theta over x squared plus y squared is r squared. So this is the square root of 25 minus r squared plus 25 take away r squared. R dr d theta. Don't forget to put your r there. Right, whenever you switch to polar, you got to do that. Now this integral is so difficult, we are not going to do this at all by hand. We are just going to make Maple do the whole kit and caboodle. Right, this is very tricky. Nothing in here is simple. All right, so here's the graph of the surface inside that vector field. If you want to look at it, there it is. And then there's the solution. It's 625 pi over 2. And you can see I actually distributed the r's in there because there's an r times everything, so I made it r to the fourth, but nevertheless, it's still pretty ugly. So 625 pi over 2, which is 981.7. So I wrote that on my paper, and that's our final result. Now, that was using the method we already learned, using a surface integral to do the flux. But now we want to practice with the divergence theorem, but we're going to do that in the next video.